Good morning. I'm Johnny Duke. I'm going to be teaching the sections on exponential and logarithmic functions and their applications. Today we're going to begin by looking at exponential functions, and in particular we're going to introduce it with a scenario. The scenario is this. Bill Gates is trying to get back into competition with the iPhone, the iPad, and other things. He's run into a glitch, and he we'll pretend that you are an expert in computer programming. And he also knows that you can solve this problem within 30 days. And so he wants to do this badly enough that he's willing to let you choose your payment plan. Let's look at the two plans that he is offering you. The first plan, we'll call Plan A, is a flat $50 million for 30 days' work. And Plan B is a little more complicated. Bill says, I'll pay you $1 for the first day, $2 for the second day, $4 for the third day, $8 for the fourth day, and so on until the 30 days are up. Which plan should you take? Now, if you're like probably 98% of Americans, you say, woohoo, give me the $50 million for 30 days work. I'll be set for life. Of course, some of you are probably looking at me and saying, well, that math teacher's a little gray-headed and he probably has some plan up his sleeve. So let's see what happens with with Plan B. So let's explore Plan B for a few moments. In this problem, there are two variables, time and money. Since time is determining how much money you will make, it's the independent variable, and we'll use standard algebra procedure from the past and let x equal time. We will therefore let y equal the amount of money. Now let's make a chart for your pay for the month, or at least for the first few days. So when x is 1 on the first day, you received $1. On the second day, you're to receive $2. On the third day, you're to receive $4. And on the fourth day, he said that you would receive $8 and so on in that pattern till the end of the month, which would be 30 days' wages. Now, as you've probably noticed, each y is doubling the previous y. So on the fifth day, how much money are you going to make? That's right. 8 times 2 is going to be 16. And on the sixth day, you'll make 16 times 2, or $32. Now, in math, we like to use shortcuts. I could find out how much money you're going to make on the 30th day simply by doubling each previous day's salary. But we always want to find a short way to do things, and we can do that in this as well. So let's go back and look at our numbers again. Each one of these y values has one thing in common, and that is that they are powers of 2. 1 is 2 to the 0 power. 2 is 2 to the first power. 4 is 2 to the second power. 8 is 2 to the third power, and remember now that means 2 times 2 times 2. And 16 is 2 to the fourth power. And finally 32 is 2 to the fifth power. What would you be making on the 30th day down here? So we're going to skip. Well, if you look carefully, on the sixth day, it was 2 to the 6 minus 1, or 2 to the fifth power. And on the fifth day, it was 2 to the 5 minus 1, or 2 to the fourth power. So on the 30th day, it will be 2 to the 30 minus 1, or 29th power. Now, that doesn't sound like a very impressive number, but let's go to our TI calculator and see how that's going to work out. So as we've got our TI-84 calculator here, we can take 2, notice we'll take 2, we'll hit the exponential button, which is the hat button that I just hit, to the 29th, and hit enter. And notice by adding commas in, we can read this number more easily, and we will have $536,870,912. Now that's your salary only for the 30th day. Basically, if we go back to our review of what we were looking at on the PowerPoint, we found out that you have over $510 million. We'll just round that off. But what we also can note is that if you add those days, say the first 3, you get $7. If you add the first 4, you get $15. $1 less than you'll make on the 5th day. If you add the first 5 days, you get $31, $1 less than the 6th day. So for days 1 through 29, you will actually get $1 less than that amount we looked at a few minutes ago, $510 million. Essentially, you will become a billionaire. Now, what's the point of this? The point is that exponential growth starts out very slowly. That first week, it looked like you were only going to make $127. 50 million looks very good. Plan A looks very good there. But by the end of the month, we've had extremely rapid growth, and you will end up making over $1 billion for the month had you chosen Plan B. Not bad for a billionaire. Now, let's continue on and look at what kind of functions are allowing us to have this kind of growth. These functions are called exponential functions. Today, we're going to introduce exponential function notation over the next few minutes. We're also going to learn terminology that's important so we can communicate with each other effectively. We're going to look at 3 ways that we can represent exponential functions, just like other algebraic functions. And finally, we're going to apply the transformations we've had before to exponential functions. So let's look first at introducing exponential function notation. In exponential functions, first of all, let's go back to this idea of an exponent. Multiplication's repeated addition. In our example here, we have 2 plus 2 plus 2 plus 2, which would be extremely boring to write out, and so mathematicians evolved that to be 2 times 4. So repeated addition is multiplication. In the same way, we wouldn't want to multiply 2 times 2 times 2 times 2 repeatedly, and we will say that's 2 to the 4th power. So we've got in general that if we take 2 times itself x number of times, then it will be written as 2 to the x. Now, how does that work out with definitions then? In function notation, we can make our f of x equal to 2 to the x. And 2 to the x gives us 2 important definitions. 2 is the base in our exponential function, and x is the exponent in the exponential function. Now, are all exponential functions base 2? That's what we've looked at so far. But actually, all exponential functions do not have to be base 2. And so consequently, we can use exponential functions that have other bases. Let's take a look at that for a moment. Okay, we can generalize by having f of x equal b to the x. Remember, b is going to be our base, which is why I chose b. And x is the exponent, which is why it's an exponential function. Our variable, independent variable, x, is in the exponent. We can generalize the base to be any positive real number. In other words, b must be greater than 0. Hence, f of x equals negative 2 to the x is not a legal exponential function. But f of x equals 3.5 to the x is an exponential function. Why? Once again, remember the base must be a positive number. Negative 2 for our base will not work, obviously, because it's a negative number. Yet 3.5 will work, even though it's not a nice whole number. It will work because it just had to be a positive real number. Now, what about the exponent? The exponent can be any real number. In other words, x, our exponent up here, can be any real number. And it's okay that it's negative. So if we let f of x equal 2 to the x, 2 is a positive note, our base is a positive number. X, we could have f of negative 2, which would be 2 to the negative 2. And 2 to the negative 2 is fine because the exponent can be negative, whereas the base could not. Or we could have something as exotic as f of pi, which would mean 2 to the pi. Once again, that's not a problem because pi is a real number that we have. Okay, so we've looked at our definition for our exponents, and we've looked at the terminology. Now let's look at 3 different ways that we can represent exponential functions. And if you'll recall from our previous algebra studies, we can represent functions analytically, which is basically by looking at the equation. We can also represent them in the use of tables. And finally, we can represent them with the use of a graph. So let's look at this as it pertains then to exponential functions. Our first representation is analytic. I can let f of x equal 2 to the x. That's just our plain old function notation. From that, I can get a numerical representation, which is a set of ordered pairs. And as you look at those set of ordered pairs, you may wonder, where did those numbers come from? Now remember, our function up here is f of x equals 2 to the x. And I'm going to start right here with 0. If I take f of 0, I get 2 to the 0, which is 1. If I let x be 1, I'm taking f of 1, which is 2 to the first, which is 2. And so on. 2 squared is 4. 2 to the third power is 8. Now let's go to negative exponents for just a moment. If I take f of negative 1, I'm looking at 2 to the negative 1 power. And if you'll recall from previous algebra classes, That negative exponent means that it is the same as 1 over 2 to the first. Hence, 2 to the negative 1 equals 1/2. And 2 to the negative 2 is 1 over 2 squared, which is 1/4. And finally, 2 to the negative 3 is 1 over 2 cubed, which is 1 over 8, or 1/8. Now, we've looked at 2 of our 3 representations. Let's now go on and look at the graphical representation. If we look at the graph of f of x equals 2 to the x, you will notice that as we go from left to right, the function x is increasing, our domain is increasing, and the function slowly increases at first. But after, say, about x equals 2, it becomes a very steep increase in the functional value itself. So what that says for us is that we've got an exponential function. Part of exponential functions are that they can increase very slowly. Remember our example with Bill Gates. The first week we worked for a total of $127. But by the end of 30 days, we were making over $500 million for one day's work. So our function increases slowly at first. Also, let's look at and review a couple of terms here. The domain of the function, if I took every one of these points and took it down to the x-axis, it would cover a point on the x-axis. If I squeezed that line down to the x-axis, it would cover the entire axis. Hence, the domain is negative infinity to infinity. Or we can let x be any real number between negative infinity and positive infinity. Remember, the range are the y values that we get when we do that. And as we've seen, 2 to a negative exponent is not a negative number. It means 1 over 2 to a positive number. Hence, the y's that we get will be only positive numbers. And so the range in this case is the range of f is 0 to positive infinity. Or if we collapsed all of those points to the y-axis, that would be the amount that would be covered. So we've looked at our analytical. We've also looked at the table. And finally, we've looked at the graph. Now it's time to practice a couple of problems on your own. And let me give you a little bit of time to do that. As you look on the PowerPoint, there is a function, f of x equals 3 to the x. I want you to find f of x for each of the values. In other words, f of 2, f of 1, f of 0, f of negative 1, and f of negative 2. And again, remember that that a to the negative n equals 1 over a to the n. Let me pause for a moment and let you try to find those values on your own. Then we will come back and work those out to see how well you did. Okay, now that you've had a chance to try those, let's check your answers. F of 2 means that x is going to equal 2. Remember, f is the function that takes any x and raises 3 to that power. So f of 2 will be 3 to the second power, which repeated multiplication is 3 times 3, or 9. Now, that gives us a point on our graph, and I hope that you put down the point 2, 9. Similarly, if we take f of 1, that's going to be 3 to the first power, which is 3. The point on our graph that results will be 3, 1. Or rather, 1, 3. F of 0 will be 3 to the 0, which, remember, any number to the 0 power is equal to 1. Hence, we will get 0 maps with 1. F of negative 1 will be 3 to the negative 1. Now we're remembering that a to the negative n is 1 over a to the n, so 3 to the negative 1 is 1 over 3 to the positive 1, or 1/3. So negative 1 goes with a positive 1/3. And finally, f of negative 2 is 3 to the negative 2, which is 1 over 3 squared, which is 1 over 9. So the point on our graph would be negative 2 goes with positive 1/9. Hopefully you did well in that practice time. Let's now change things slightly. If you'll notice on this practice, we're going to let f of x equal 3 to the negative x. We're going to let our exponent be negative to begin with. So let me do one for you, and then you can practice the others. F of 2 would be equal to 3 to the opposite of 2. But we just saw on the previous example that that is 1 over 3 squared, which is 1/9. Hence, our point on this graph will be positive 2 goes with 1/9. F of negative 3, f of x equals 3 to the negative x, when we look at f of 1, will be 3 to the negative 1, which is 1 over 3 to the first, which is 1/3. Hence, we will get 1 goes with 1/3. Let's let you try the other 3 of those. Let's see how well you did. In this case, we can take f of 0 will be 3 to the 0, which simply again is 1. So our point 0, 1 is also on this graph. Now, as you do graphs, you'll notice this is a point that is on almost all exponential curves. As we look at f of negative 1, that will be 3 minus negative 3 to the minus negative 1, which will be 3 to the positive 1, which is 3. And so now negative 1 is going with positive 3. And finally, I hope that when you did f of negative 2, you got 3 to the minus negative 2 and realized that is just 3 squared, or 9. And so negative 2 will map with 9. And that will be a point on our graph. Now, let's explore what happens as the base changes from 3 to 0. Now, before we look at that, remember that if we have y equals the log base b of x, in our definition, b had to be greater than 0. But there's one value for b that's an extremely important value, and that is b equals 1. Think about it. If b equals 1, then we get y equals the log base 1 of x. Using our equivalent exponential statement, that would be 1, our base, to the y, what it is equal to, is x. But remember, 1 squared would be 1 times 1, which is 1. 1 cubed would be 1 times 1 times 1, which is 1. 1 to any power actually is going to be 1. And so consequently, that means that y equals the log base 1 of x is always going to be y equals 1. And we'll see that just a minute when we do our graph with Geometry Sketchpad. But what we're particularly interested in this animation is what happens to our graph as our base is greater than 1. We'll start about 2.99 with our base, and it will go down to 1. We'll see it flatten out. And then what happens as our base becomes less than 1, but at the same time, remember, has to be greater than 0. So let's look at our animation on Geometry Sketchpad. On Geometry Sketchpad, we're starting with f of x equals 2.8 to the x, so our base is 2.8, and look, our curve looks like what you've come to view as a normal exponential curve shape. Now let's animate. Notice as our base gets smaller and smaller and gets closer to 1, the curve flattens out. And that's exactly what we said was going to happen. When our base equals 1, we really don't have an exponential statement as much as we have a linear function. Now, let's continue the animation and look at our base when it is less than 1. Notice it goes over to the other side of the y-axis. And so it's reflected essentially through the y-axis if we have a base that is less than 1. Let's look at that one more time. There's where we have our base around 2.7. It's getting closer to 1. Our curve is flattening out again. And then after it goes below 1, it makes the curve a decreasing function. Now, as we go back, let's look at a very important value for b. This one we're going to use in our applications a good deal. That value introduces a number that you may not have heard of before. It's called the natural exponential base, or base e. It seems unusual for us to have a number that is given, a specific number that is given by a letter. You probably already know one number that is given by a letter, and that number, of course, is pi. Pi equals about 3.14. It's an irrational number, meaning that in decimal form it does not terminate, does not repeat. Hence, we cannot write the entire number, and we use a Greek letter, pi, for that. Well, the same thing's true with the number e. E is a number that is about 2.71, and hence it lies between 2 and 3, and it is called the natural exponential function. So we can have f of x equals e to the x. Essentially, what we're saying is approximately it's equal to 2.71 to the x. Let's look at finding some particular values for this function, and we'll use our TI-83 calculator. We're going to look at what is f of negative 2, f of negative 1, f of 0, f of 1, and f of 2. Now remember f of 2, since f of x equals e to the x, f of 2 will be e to the negative 2. And we can find that on the TI-83 calculator. As we look on our calculator, on the left-hand column, there's an LN button. We'll be talking about that later. But above it is e to the x. So we hit second, e to the x, And then remember, we want negative 2, e to the negative 2. So we use the negative button, remember, at the bottom of the calculator, not the subtraction button. Otherwise, you'll get an error. So negative 2 is, in fact, 1.135355, and it goes probably out to infinity in this case because it's an irrational number as well. Okay, so we found out how to do that on the calculator. Let's go back and finish these others then. And as I'm looking at this on the PowerPoint, you can be working along with me on your calculator. So let's take f of negative 1. Now remember, once again, f of x is e to the x. And so at this point, we'll be taking e to the negative 1. On your calculator, you will hit second and ln for e to the x, put in the minus at the bottom, negative 1 equals 0.368, rounded off 2/1000th place. Now the next one we don't even really need the calculator for because f of 0 is e to the 0. Since e is a number, e is just like any other number to the 0 power, that is equal to 1. If you wanted to check that on your calculator, you would hit second, ln, put in 0, close the parentheses, hit enter, and naturally you will get 1. The next one's important because e to the first power is nothing more than e. So we're about to get a decimal representation for the number e. If you look on your calculator, hit second and ln, put in 1 for e to the 1, close the parentheses, and notice you get to several places after the decimal an approximation of e. I'm going to stop at 5 places after the decimal, but it's about 2.71 or 2.78. And finally, if we take f of 2, that would be e to the second. And again, on our calculator, second ln to the second, it equals, and we get 7.389. So we've learned an important function that we're going to be using over really this entire section or chapter with natural exponential and natural logarithmic when we get to the logarithmic functions.